Get rid of the pixels. Okay, so it's week 3, and we're going to do energy storage and distribution. And I have received just about everybody's assignment 1. I want to highlight this particular solution set. It's the tidiest one I've ever seen. So, gas tank, car battery, beer, baked chicken, cell phone, calculator, etc., etc. I love this. That's the amount, there are the units, and there's the conversion. Some of it's a little bit buried, but this is okay. We can come in here and see what he's done is gone with gallons to BTUs and BTUs to kilowatt hours. So it's kind of, it's super tidy. I mean, everything is right there in one little package. And I think, pretty cut and dry. Everything is either, so that's chemical, electrical, chemical, chemoelectric, what are you gonna call it? Electric, chemical, thermal. And I do want to do the thermal problems. I think a few people, this came out a little bit weird in some cases on the units conversion. This was like the trickiest one. So we've got 100 gallons in the tank, and somewhere, okay, so over here he did his water heater problem. Said we're going from 50 to 100. And he's done everything in, well, I guess he's just gone ahead and multiplied it this way. So let's just look at this. So hopefully the screenshot is coming in loud and clear. If not, I'll just kind of describe it out. Hey, how's it going? So
what's an IBM?
An IBM is a pound. It's 1 pound of mass, LBM. So in the empirical units, though, you either have pounds of force or pounds of mass, and a pound of mass weighs a pound of force, for example. A slug of mass weighs 32.2 pounds, just kind of for the record. So, so with this, let's just kind of do sanity check first. The more gallons I have, the more energy I'm going to have. So that's a good thing that gallons is in the numerator. This guy here, G14, is pounds per cubic foot, which tells me that the more dense the fluid is, the more energy I have. That makes sense. Now let's look at the numerator. So if I have so G13, actually, hang on, G14, that's density. Let's back up 1 second. Let's back up 1 second. Yeah, density is in the numerator. Okay, and then he's got gallons per cubic foot. I really wish I had my my bamboo with me right now. I just don't.
Your cubic feet are going to cancel. Just that right off.
Yeah. Okay, so here's the problem with this. What he does not have in here is BTUs per pound per degree Fahrenheit. The fact of the matter is the answer is 1. So that I think it all works out in the end. But in order to get this more correct, you'd have times that guy. So I've actually included, you can see I went up here and I included the BTUs.
So you can make your cancellations in the BTU.
Yeah. So let's just go through it one more time here. Yeah, so now you can see I have, now I have BTUs in the numerator. This guy, G14, has pounds of mass in the numerator. It's got cubic feet in the denominator. So when I divide by gallons per cubic feet goes into the numerator, gallons is now in the denominator. That's good. And then let me pause for 1 second. I'm feeling this. Okay, so what we're still looking at here is the conversion, and it looks like Sean's just taken a few extra steps here. The number could be correct. We'll verify that. So what we've tried to do is tidy this up a little bit. So this is actually I'll add one insert rows above. So this is the specific heat of water, and the specific heat of water is 1 BTU per 1 pound per 1 degree Fahrenheit. This is the volume, and this is the mass per volume, or the density. This is our delta T, and this is our kilowatt hours to BTUs. That's our conversion. So this is just, all we're doing here is just multiplying these guys out. So at this point, I'll just hit the calculator. And we'll start with 110 minus 50, which is 60, times 100 gallons, times 8 pounds per gallon, equals 50,000 BTUs, that seems about right, times 0.000293 equals 14 kilowatt hours. Let's see back here. Yeah. Okay. And so here's what I want you to do for a problem like this. So I'm at my house, and I know that my house runs at about a kilowatt. This course could just as easily be called power storage and distribution, but it's called energy storage and distribution. So the water heater is storing that many kilowatt hours of heat. Most houses, it's another thing just to keep in your back pocket, house electricity average power is approx 1 kilowatt hour. So what this is, that's just for electricity. So
what's our timing? How long?
oh, I'm sorry.
1 kilowatt.
1 kilowatt. A house runs at about 1 kilowatt, approximately 1 kilowatt. So in 24 hours, you consume about 24 kilowatt hours per day. So let's write that out. Or approx 24 kilowatt hours per day, right? Now, house, at least in Montana, heat average power is approx 4x to 5x electricity demand. Now, so you look at this number, 14 kilowatt hours, like, well, okay. I mean, I could just about believe it. If I was running that on electricity, my water heater would have to run for 15 hours to do that. If I ran it on gas, it's coming in faster, hotter, or whatever, I might have to run it for 3 hours. to do that, to hit that delta T. So just a good sanity check there. And a lot of
You
people.
can check the density of the energy in the gas and see that it's not going anywhere but the same places.
Yeah, later in the course, we'll get to energy density of natural gas. That's a good problem too. Okay, so that's a good one. I like the way Sean put that together. File, close, save, sure. File.
It helps.
So let's look at another one here. Shauna, did I have a couple corrections on yours? One or two? Let's just take a peek here. I think I had one or two on yours too, Gary. And they were kind of common, easy to make errors. Yeah, this is. I mean, it's the same problem right here, where I don't think you. So 10 gallons of water.
Is there a delta T?
No.
Yeah, right. There was my question mark. So I didn't see where you got the delta T. So this is that same exact problem.
I'll fix it.
Perfect. And I assume you went and found that 91,000 BTUs. Okay. Well, it seems like a lot, but let's just. And then you took. Oh. Well, yeah, I don't think that kilowatt hours per BTUs, because see in this thing you've got pounds and pounds in the numerator,
Yeah, I just saw
And
that.
and you got gallons and gallons in the denominator.
That's what I just saw.
But I can actually smell propane right now, so
It's got to be coming from somewhere.
it's gonna come from somewhere.
Look that one over too, and really the way to do it is to. I mean, I'm not going to say this is the one and only way, but this is.
Analytical algebra.
It's just kind of foolproof. You know, it's pretty hard to. Pretty hard to argue with this once you start going through and then just doing this, you know, strike through pounds, cancel, BTUs cancel, gallons cancel, degrees Fahrenheit cancels, So, for me, it just works. Like everything's just on one line. Everything, then all the units cancel, and you're just left with your kilowatt hours right there. So I would look at that guy. I mean, this is just foolproof. Left to right, multiply it out, and take care of the units. Okay, and then this one. Where's that coming from? That was my question.
Google. Being honest.
Really? 10,000 BTUs now.
Per pound of coffee. Where did
Now,
Brewed coffee or?
I mean, I would believe that to harvest it, to ship it, to grind it, to heat it, you might spend 10,000 BTU. I mean, I would believe that, but I wouldn't believe there's that much energy stored in a pound of coffee. Okay, unless you're going nuclear. But I would
How
believe.
many calories are in coffee? Are there any calories in coffee?
So now we have to know the embedded energy in caffeine, because that was.
I think caffeine gives you the ability to burn calories. I mean, I think it's like the,
Opens your pathogens.
yeah.
affect your atoms?
I'd say it's a catalyst, but I'm not sure that there's really any calories. That's the question there. So I don't.
Anybody do milk? Speaking of cows?
I haven't seen milk on it either.
Because I mean, there's gotta be a whole huge difference
Pound of
between
cheese.
like whole milk and fat-free milk.
Oh, yeah.
Pound of cheese.
Lots more calories in
Because
that.
if you look at the milk under a microscope, you can see like the actual milk and then the little globule
Oh, yeah.
of fat.
Heck
which
yeah.
is triglyceride.
So fix, you know, just put something else, well, do milk. You know, or just do a food that you would actually eat for calories, because you would not eat coffee for
Pound of
calories.
cheese.
Pound of cheese.
I did ass cheese.
You did ass cheese?
Yeah, I call it ass cheese. It's Asiago cheese, and I just call it ass cheese.
Oh, I thought it was like you're going to the gym to burn
Right.
your tushy off, yeah.
Making it small.
Yeah.
No, that's basically the milk thing, but I did that one too.
So again here, this just seems a little high.
I actually just fixed that one.
Okay, good, good.
And yes, it's way high.
Okay, and then,
That was the first time I questioned you, was that the water heater was like, all right.
one,
I don't know what it's doing, I missed it.
1 pound,
It was this right here.
PDF came up super quick.
are there,
The Delta T.
are there,
Start with
90 was.
100 servings.
I think this is 0.4, isn't it?
No, it's 4.1. 4.18.
Was it about 300 gallons of water?
Do you-
Jesus, that's the biggest water heater I've ever seen.
I live in an apartment complex, it's over 75 units per
Did,
tank.
did you see what I just did there, Shauna?
You
Yeah, that's
changed my
what's so better.
four,
Yeah, because it's, and then here's another thing. And joules are always lowercase.
I know, you kept.
Calories are sometimes upper, well, calories are sometimes upper or lower. Kilocalories uppercase, lower,
That was
Single calorie.
confusing on that thing.
so,
It's just, I don't know, but my mind just wants to capitalize.
but now the next question is it 4.1 joules per kilocalorie or 4.1 joules per calorie, small calorie?
I think it's big C.
I think so too.
Okay, so I think we've done that, and I got one more. So Sean, you're gonna fix that. Okay, so this is the one that was, so square feet of house, outside temp, inside temp. What's that guy? Specific heat of what?
That's a heat capacity of probably 1 square foot. That's 70
Oh.
degrees.
At 70 degrees?
Yeah, the heat capacity once, that would be cubic feet, there's a cubic feet.
Yeah, so that's the issue I'm having here is I don't know the volume of the air in the house. So let's just do it this way. I'll just copy the thing right here. Copy it. Paste it. House height. Let's just say it's 8 feet. 12. Okay, 12 works.
This is the one where you were standing on the water?
This will be in feet cubed. This will be in feet cubed. And let's just. And now, okay, so that's equals that times that. Okay, so that's 8,500 cubic feet of air. There's the outside temp, there's the inside temp. Now, let's do the heat capacity of air. I know it's, yeah, so if we do, this is kilojoules per kilogram Kelvin. So let's run it this way. C sub P, was it kilojoules per kilogram Kelvin? Yeah. Kilojoules per kilogram Kelvin. And I'll just say, let's just say 1.003. And from there, so from here, what I have to do is get the air density. Actually, let's do air volume. Let's do house volume in cubic meters. It's 29 or something, so we'll do cubic feet to cubic meters. That'll work. 0.028, I think we just copy this guy, copy. Cubic meters per foot cubed. There's that. So the volume equals that times that. Okay, so now we've got the cubic meters. Shawnee, you like to use this thing, right? Nope, that
Right
one.
there.
There we go. 242 cubic meters. And now we want the air density. This is going to be kilograms per meter cubed. It's something like 1.02.
Sea level.
Air density 1.2. Let's just grab it. That's kilograms per cubic meter. Boom.
You
Boom.
said that's at sea level?
Yeah.
How much does it change between, say, 0 and 4,000?
There's a full table of it, you know. Yeah. But, and again, we're only going to worry about 3 significant digits anyway, and it's not going to change by more than 0.1%. Okay, so here's insert, fill this down. This is house air mass, is going to be in kilograms, equals the volume times the density. I believe that, 300 kilograms, 600 pounds of air in your house. Okay.
Yeah.
For how many square feet?
712? Yeah.
No,
Yeah. So the storage in joules is going to equal, it's actually being kilojoules, so it's C sub P times the mass times the volume. No, times the delta T. Times dink minus dink. All right, so I've got heat capacity times the mass times the delta T all day long. Joules per kilowatt, that seems correct. Actually, you know what, this is kilojoules, isn't it? Because this is kilograms.
But when you abbreviate joules, do you leave it uppercase or lowercase?
yeah, that right there is why I get confused with the
Kilojoules is uppercase, but you to write joules.
Yeah, all units.
Divide 16, I-16 by, or I-18 by I-16. Because you can, it's a proportion, you can switch the joule per kilowatt hour around, kilowatt hour per joule.
Yeah,
Can we divide?
We're in kilojoules now.
Let's check it out. Hang on, let me get this.
Oh, I see what you were saying.
It's actually 3,600 kilojoules per kilowatt hour, right? Okay, so the deal on units.
Okay.
Here's the deal on units. Glad you asked. So newtons is N. Joules is J. Kilowatt hours is kilowatt hours. Watts. What else?
Newton's is Newton times meter, isn't it?
Meters
Meter in there.
is M.
Well, it would be a newton meter.
Yeah, degrees,
Joule.
That's a joule, yeah.
Celsius. The only weird one is Celsius. Celsius is the only one with the capital.
Oh.
I can never spell it. Is C, and it's written out as Celsius. Degrees Kelvin. So it's the same way with nitrogen. You don't capitalize nitrogen, but you capitalize the N.
Welcome to the English language.
Well, it's very easy because this part is never the word is never capitalized. There's only one exception, and it's right there. In the whole, it's the only one I know of. It's the only exception to any of that.
Meters is lowercase.
Yeah, meters is lowercase. Well, meters is not named after anybody. There's no Sir Meter. Or Sir Second.
Oh, now, Mr. Engine.
Yeah. Okay. So that was the main deal on these guys. 2 kilowatt hours. Does that seem reasonable? Couple hours to get your house up to temp? Yeah. Couple hours.
The delta T was pretty small,
Yeah.
30 degrees. Oh, no, that's Celsius, so I guess I figured that.
70 Celsius is cooking.
Yeah.
All right.
130.
So that's enough.
I see what I did wrong.
Okay.
I just did it at 70 Celsius. I didn't do any temperature difference
Okay.
from outside to inside. I just looked at 70 Celsius.
Oh, okay.
Ah.
Okay. Yeah. All right. So that's good. We're going to put a fork in problem set 1.